we now know what L sub P of omega looks like as omega varies from DC or 0 up to infinity. It starts out of a certain length, basically the hypotenuse from determined by this right triangle with one side having a distance a and the other side having a distance of omega naught. It then reduces in length until it gets to the frequency omega naught. And then as omega sweeps beyond omega naught, L sub p begins to lengthen again. And based on that insight, we are now able to sketch how the magnitude, the linear magnitude, this is not the magnitude of h in dB, this is the linear magnitude of h. It now is this ratio of k, which is a fixed number, divided by L sub p, and we now know what L sub p does. It starts out somewhat long, then it shortens, and then it lengthens again. And because of that decrease and then increase in length, our sketch for the shape of h of j omega from DC up to higher frequencies, now right here at this frequency omega naught is where L sub p is at its minimum, and that's going to mean that this ratio of k over L sub p is at its maximum. And because of that, we can now say that frequencies that are near the pole's imaginary value, which is omega naught, those frequencies, those omega values near omega naught are now enhanced, or I might say favored, relative to other frequencies. And I think it's clear that if you were down at this frequency, maybe omega 1, the way that h responds to a signal at omega 1, it doesn't respond as well. The signal is not as enhanced as if the frequency was at omega naught. And that's what we want to understand now about poles. Poles allow us to enhance or favor frequencies near those pole values. What I would like to say also is we actually made an assumption, or we built that transfer function h out of a one pole system where that pole was complex, but making that complex pole assumption really didn't negatively impact or influence our qualitative behavior of the description of the magnitude of h of j omega. If we had included, so making the complex single pole assumption is not very restrictive relative to the qualitative behavior of the magnitude of h of j omega. If we would have had the twin pole down below at minus a minus j omega naught, that distance, or the way that that pole would have influenced the overall magnitude, it would have just introduced a length that continues to increase. It's just monotonically increasing from DC up to infinity. And that doesn't really change this favoring behavior that we see out of h of j omega when we only introduced or allowed a single complex pole. Let's now talk about using this knowledge that we have about gain enhancement due to a pole to talk about building up low-pass filters or creating a low-pass filter. If we think about what we want to have happen in an ideal case relative to omega, if we had a low-pass filter, and now I was asking you to sketch the shape of the magnitude, the linear magnitude of h of j omega for this ideal filter, then you would say, well, at low frequencies, I want those frequencies in the pass band to pass unchanged. I want the magnitude to be 1, and then any frequencies beyond the cutoff frequency of my low-pass filter, I want those to not get through the filter. I want their magnitude to be 0. That's now the ideal behavior of a low-pass filter. If we now translate that back into what we learned about poles, now what do we want to do? Well, we actually want to create a filter that will favor all of these frequencies from DC up to omega naught. We now want to favor each frequency out to omega naught, and then we want to quit favoring frequencies that are higher than omega naught. And let me say, and then stop favoring. If that's what we want to do, now does that give us any intuitive feel for how we would build a low-pass filter by placing poles in the complex S-plane? If we now wanted to build a low-pass filter that passed frequencies up to omega naught, what could we do to locate our poles? Well, if we want to favor frequencies up to omega naught, and if we wanted to favor omega naught, we would put a pole there. And we wanted to favor all of those frequencies between DC and 0. And obviously we have their cousins or twins down below, and we're down here at minus j omega naught. What the textbook does is it calls this collection of poles, that pole pattern that will favor all frequencies from DC up to omega naught, it calls that pattern a wall of poles. Now, we're not going to create an infinite number of poles in our filter. We're engineers and we have to basically make trade-offs. Let's now just look at what would happen if we tried to approximate that idea with something that's a little bit more realistic. Let's now approximate the wall of poles. What's the structure going to be? And let's just pick a particular frequency for our bandwidth. Let's say that we now are interested in omega naught being 10 radians per second. Instead of having an infinite number of poles, let's just say we have 5. Here's J10, and here's minus J10. If we have 5 poles, let's put 2 of those poles, and if we have complex poles, they have to come in complex conjugate pairs in order to give rise to real coefficients in our resulting transfer function. And we have another pole, let's say at minus 10. Well, let's just put another pole halfway between. Meaning, let's just now build up a filter that has a pole at minus 1 plus J10, another pole at minus 1 plus J5, another pole at minus 10. That's not what I wanted to say. This one now is at minus 1. If I could erase that. than the other one. So we're not, this is not drawn very well to scale, is it? Let me erase this, and now that's -1. Maybe what I should do is erase this line and bring this over so that it looks a little bit better relative to what I'm trying to draw. This is now J10, here's J5, here's minus J5, and here's minus J10, and I'm only now -1 into the left half plane. This is now -1 plus J5, and this is -1 minus J10, and that should be right here a minus J5. What would that look like in terms of its frequency response? And since we can play with MATLAB, and I will include the code at the tail end of this lecture, but let me just show you the picture that results. This is now the magnitude response of that wall of poles for a fifth order filter. If we created a filter with those 5 poles at -1 plus and minus J10, -1 plus and minus J5, and -1, this is the behavior that we would obtain for the linear magnitude of our transfer function h. What if, well, that looks a little bit rough, doesn't it? What if we tried a different pole pattern? What if we said, well, we want to favor poles up to 10 radians per second. What if we had a pole right here at -1 plus J10, and obviously we have its twin down here at -1 minus J10. But then let's put another pole out here at -10, and if we sort of connected these with a straight line, we could say that this one now, if this is J5, maybe this is now -4.5, since there's 9 steps between -1 and -10, -4.5 plus J5, and now we have its conjugate down below, which is -4.5 minus J5. What does that look like? Here I'm going to call this pattern, this pole pattern, maybe a linearly varying pole pattern. And what I'm trying to do is smooth out my magnitude response, not have so many jumps or bumps on it. If you now sketched this pattern, now, oh, it does look a little smoother between DC and maybe 7 radians per second, but because of these poles at -1 plus and minus J10, yes, it's getting us something to be passed at 10, but it's also introducing a pretty big bump at 10, meaning it gives us some resonance behavior out there, and we would like to maybe smooth that out and not have so much bumpy behavior between DC out to 10. What we would really like to have is something that's closer to the ideal. Remember what the ideal was? We'll try to practically approach that. Here is the ideal behavior. We had our linear magnitude h of j omega, and we said linear, or ideally we would do something like this for our pattern as a function of frequency omega, where this is now, let's say, our bandwidth omega naught. If we just had a first order filter, then we know what that's going to look like. It's going to have a DC gain that we want, and then it will roll off. As we increase the filter order, we're going to allow that magnitude to remain closer to the ideal for longer. And actually what I should have done is made this curve do that, meaning the first order does not roll off as quickly as the higher order, and as we are increasing the order of our filter, n, where n is the number of poles, the more poles we introduce, the closer to this ideal behavior we are going to obtain or approach. And what we are trying to look at in one filter approach is to say, what if we wanted to be maximally flat in the pass band and be pretty close to that ideal shape or behavior? Here what you will want to do is then create a filter that has poles in a Butterworth pattern. And now if you do any kind of shopping, or if you like breakfast and syrup, maybe you think of Mrs. Butterworth and you put syrup on pancakes, so now you have this flat as a pancake idea. The Butterworth pattern now is for flat filters. That's what you can think of when somebody says, oh, you have a Butterworth pattern of poles. Now you can think that that means, oh, they now have a maximally flat pass band behavior for the particular filter order that is given. And in our particular case, if we now looked at what's happening with a Butterworth pattern that's fifth order, this is now the maximally flat behavior that we want. Let's now see if we can produce that or build that up for any filter order n that somebody suggests that we have. Here's the process that we will follow to find Butterworth pole locations and building up Butterworth filters. Suppose that we now wanted a first order filter, and for now let's think of all of these filters having the same bandwidth. We'll just call this our normalized filter design, and our normalized filters will have a bandwidth of 1 radian per second. We will then talk about how we can scale those to be any bandwidth that we want, but for n equal to 1, how would we produce a transfer function? What would the transfer function look like? It's a low-pass filter. That means all we want are poles. We don't want any finite zeros. Let's just make our numerator factor be 1. It's a constant. Now what we want to do is we want to have a bandwidth of 1 radian per second, and we want a first-order filter. If we want a first-order filter, we now know that we need a polynomial in the denominator that is only first order, meaning we just have an S term. Going back to what you know about Bode plots and bandwidth, if we want our low-pass filter to have a bandwidth of 1 radian per second, what does that mean about the denominator polynomial? Now we want that denominator to have a pole at -1. We only have one pole. It has to be real, and that real pole will be located at s equal to -1. Now what we're going to learn in order to build up Butterworth filters is we can rely on a particular formula, and that formula takes the 360 degrees in a circle, and it's going to now position poles to give us our Butterworth pattern that are symmetric with respect to the origin. That means it's symmetric with respect to the real axis, the horizontal axis, and the poles are symmetric with respect to the vertical or imaginary axis. To make that happen, we take the filter order, little n, multiply it by 2 and divide that into 360. For this first case, with n equal to 1, we now have 360 divided by 2, or we now have 2 poles in this Butterworth pattern of 360 degrees, and we are going to separate those 2 poles by 180 degrees so that our pole zero pattern for a first order Butterworth filter that's normalized to a bandwidth of 1, now we have an angular separation between those poles of 180 degrees. The poles have to be symmetric with respect to the origin, and for a Butterworth filter, what we are doing is we are actually wanting to have a stable system, and the Butterworth filter is really specified in a way that works with this magnitude of h of j omega quantity squared. And what it will end up being is you will find that if your poles are symmetric with respect to the origin and they have this Butterworth shape, you will now have the magnitude of your transfer function squared being 1 plus omega to the 2n. And this is for omega naught equal to 1 radian per second for normalized filters. To make that shape happen, what we do is we will now have 2 sets of poles. A set that's in the left half plane and a set that's in the right half plane. Since we are squaring this, we have 2 h's. We want to pick the h that only has the negative real part poles, or we want to build a stable filter with a Butterworth pattern. Let's now look at what we could do if somebody said build up a second order Butterworth filter. N is now equal to 2. Our formula is 360 degrees divided by 2n, or 360 degrees divided by 4. This now 90 degrees is the separation between all of our poles in the complex plane, with half of those poles being in the right half plane and the other half being in the left half plane. And our Butterworth filter is only going to pick the stable poles, or those poles in the left half plane. Now we want to have stable transfer functions, and if we now have 4 poles in total in the complex S-plane, and we want them to be symmetric with respect to the origin, and the poles are 90 degrees apart, we can't have 2 poles on the imaginary axis. But if you thought about those axes and just rotated that 45 degrees, you could now envision what's going to happen with respect to the 4 poles. These 4 poles, because we are doing the normalized filter, we are now locating all of our poles on this circle that's a distance of 1 from the origin. That's the radius of this circle. And what we are doing to build up the Butterworth is we're only going to retain the poles in the complex, or in the left half of the complex S-plane. And what we just said is the separation between these poles is 90 degrees. This angle is 90 degrees. This angle is 90 degrees. All of these poles are the same angular separation from each other, and they're all 90 degrees apart. And they are symmetric with respect to the origin. We don't have any that are on the real axis. But to be symmetric with respect to the origin, that's saying that we have to split this 90-degree angle in half and put half of it above the left or the negative real line and half of it below. And now that we know where those poles are, we can find their particular value. This pole is now 1 away from the origin, and it's at a 45-degree angle, which means that it has a real part of 1 times the cosine of 45 with a negative sign, and that's just minus the square root of 2 over 2. The imaginary part is now the sine of 45 degrees scaled by 1, and so it's now going to be plus j square root of 2 over 2. It has the equal real and imaginary piece. Likewise, this particular point is now minus the square root of 2 over 2 minus j, the square root of 2 over 2. What can we say? Well, the poles in this process need to remain symmetric with respect to the origin, and we're going to build up these pole patterns with twice as many poles as we need, and our filter needs to be stable. And what we do then to create the Butterworth pattern for our low-pass filter is we only want to retain the stable poles. So that now if we wanted to build our transfer function, h of s, we would say, okay, we have our numerator, which is 1, and now we have 2 poles. We have 1 pole in the second quadrant, and we have another pole in the third quadrant. If we multiply those 2 pole factors together, we will see that we have one of these standard forms that I like to write my complex factors in terms of. We have s plus the real part quantity squared, or really s minus the real part, since our real part is in the left half plane. We then have s plus its length quantity squared plus the imaginary or the damped frequency squared. That's now h of s. And if we multiplied all of that out, then we would have s squared plus 2 times the square root of 2 over 2 times s. The 2's cancel, and we have the square root of 2s. And then we have the quantity, the square root of 2 over 2 squared, plus the quantity, the square root of 2 over 2 squared. Both of those are 1/2. We add those 1/2 together, and we end up with 1. That's now our second order low-pass Butterworth filter that has a bandwidth of 1. What if we wanted to build up a third order? We just use our formula, 360 degrees divided by 2n. N is now 3. We now have 360 divided by 6, or that's now 60 degrees. We now know that all of our poles need to be separated by 60 degrees. We're going to have twice as many poles as we need in the overall complex S-plane, but we're only going to pick or retain those poles that are in the stable part of the S-plane, which are in the left half plane. Now we have an odd number of poles, which says that one of our poles is going to be at -1, and we know that all of the poles are separated by 60 degrees. We can now go 60 degrees away from that pole and say we're 1 away from the origin, and that's now our location for one of the poles in the complex left half plane. Here's another 60-degree angle. We walk along that radial line a distance of 1, and there's our other pole. And likewise, we could, if we wanted to, we really wouldn't have to keep putting all of these together, but now we just mirror those stable poles across into the right half plane to give us all 6 poles, and this is now our 60-degree angular separation between those poles, 60, 60, and 60. And here are the 3 poles in our third order system that we would retain to build up our low pass Butterworth filter that has a normalized bandwidth of 1 radian per second and it's third order. Let's do one more example. N equal 4. I think you're starting to get this. 360 degrees divided by 2n. We now have 180 divided by n. N is 4. We now have 180 divided by 4, or 90 divided by 2. That's now 45 degrees. We now have a total of 8 poles, all divided or all separated by 45 degrees. N is even, so we do not have a pole on the real axis. We now have to split that 45 degrees in half and go up 22 degrees and over 1 along that. Here's now a 22.5 degree angle, as is this angle. Now we can go up here 45 degrees from that angle and go along that radial line segment, or ray, 45 degrees. And those are now our 4 poles. And again, we are a distance in this normalized setting. We are a distance of 1 away from the origin. And that gives us our omega naught. And this then is at -1 where that goes through. And I've already shown you what the picture looks like if we were to sketch in MATLAB the magnitude response for a 5th order. Now we are quite flat out until we reach nearly 10 radians per second, and that's where we start to fall off and roll off. Let's now go more specifically into, or with a little bit more detail, the design of a 3rd order filter. And we now want to design a 3rd order low pass filter, and we will actually build this up normalized to begin with. We want to find where those poles are located, and then we will scale that design so that we could then create a 3rd order low pass filter that has, let's say, a bandwidth of 10. But before we do that, let's now build up the normalized 3rd order filter. We know our angles are separated by, or our poles are separated by an angle of 60 degrees. We have an odd number of poles. That means that one of the poles can be on the real line. We now go away from that pole, the separation angle, which is 60 degrees. We move along that radial line a distance of 1, and we do the same thing in the 3rd quadrant. And what we now want to do is locate these different poles. Let me call the real pole S sub 1. In the 2nd quadrant, let me call that S sub 2, and in the 3rd quadrant, S sub 3. We know for the normalized filter that S sub 1 is at -1. We also because of our trigonometry, we can find the real part of S sub 2. We now know that we could project that location and find its real part and its imaginary part in terms of the length. In this case, we have minus 1 times the cosine of 60 degrees, and that's now minus 1/2. The imaginary part of S sub 2 is 1 times the sine of 60 degrees, and that's this square root of 3 over 2, which says then that we have S sub 2 is equal to minus 1/2 plus j square root of 3 over 2, and S sub 3 is equal to minus 1/2 minus j square root of 3 over 2, because we know S sub 1 and S sub 2 are complex conjugates. Or if we wanted to write that out not in fractions but in a decimal manner, we now have minus 0.5 minus j 0.866, since the square root of 3 is roughly 1.7, a little bit more. We now have S sub 3 is minus 1/2 minus j 0.866. We can now put that into a transfer function, h of s, which is 1 over, and now we simply put all of these poles together. We have s minus s1, s minus s sub 2, and s minus s sub 3. Those values for the s's will cause the denominator to vanish, which is what we want for our poles. H of s is now 1 over s minus a minus 1, and then let's go ahead and just write s minus s sub 2 and s minus s sub 3 in the real coefficient form that I like to use. We take the negative of the real part, which is then 1/2, and we say s plus the real part 1/2 squared plus the imaginary part squared, and that will now produce the following factor in the denominator. We now have s squared plus 2 times 1/2 s, or that just gives us plus s. Then we have 1/2 squared, which is 1/4, and then we have the square root of 3 over 2 squared, which is 3/4. Or this piece, the constant piece, is simply 1. H of s now becomes s plus 1 times s squared plus s plus 1, all in the denominator, or dividing into 1. And if we multiplied those two factors together, we would find that we have now a third order, an s cubed, plus 2s squared plus 2s plus 1. This is now a third order low-pass filter with a bandwidth normalized to this 1 radian per second. And as I've said, we probably don't want to always be living with a bandwidth of 1 radian per second. That would make for a pretty boring world, and we probably wouldn't have to hire too many filter designers to satisfy everyone's needs. We want to now frequency scale, or be able to now convert those normalized filters into whatever bandwidth we want them to possess. Suppose that we now want a bandwidth of 10 radians per second to be consistent with what we looked at via the MATLAB material before. I'm now going to call this 10 my capital omega sub n, and in order to frequency scale these normalized transfer functions, what we will do is everywhere we have an s, we are going to replace that s with this ratio, s over omega sub n, which in our case, we said let's go ahead and make our bandwidth 10 radians per second. We now have s over 10. Our denominator now is going to be this s over 10 quantity cubed plus 2 times s over 10 squared plus 2 s over 10 plus 1. We've simply replaced all of our s's with this denormalizing factor s over 10. This now will provide us with a new transfer function. I'll call it h sub 1 of s, which is 1 over that denominator, but that's kind of a mess because now we have a ratio of terms in the denominator. We probably just want a ratio of polynomials. We can actually get rid of that denominator mess by looking at what power of 10 is the largest that we have down there, and it's actually 10 cubed. Let's now multiply by 1, which we can do, and that's just 1,000 over 1,000. If we now multiply that expression, 1 over denominator, by 1, then we will end up with h sub 1 of s being equal to, we now have 1 times 1,000 in the numerator, then we have s cubed over 10 cubed times 10 cubed, or simply s cubed. We have 2 times 1,000 times s squared over 100, or we now have 2 times 10 s squared. In the next term, we have 1,000 divided by 10, or that gives us 100 times s. And finally, we had the 1 times 1,000, and that's now just 1,000. And this is what we probably would prefer to have, is some non-normalized low-pass filter. This h sub 1 of s represents a low-pass filter with a bandwidth of 10 radians per second. What we want to do now is actually turn that into a state space representation. What we have time for now is really just creating a differential equation relationship between input and output for that filter. H sub 1 of s, that transfer function, is simply this ratio of the output's Laplace transform to the input's Laplace transform. We're going to take this transfer function into a differential equation. That's all we will get to in this lecture, but once we have it in the differential equation form, we will create an all-integrator block diagram, and once we have an all-integrator block diagram, we can simply assign states to the outputs of those integrators and obtain a state space representation. We want to now go into the time domain from the frequency domain. We have a frequency domain relationship between the input and the output in that transfer function. Now if we cross multiply, we have s cubed plus 20s squared plus 200s plus 1,000. That's all times the output y of s, and that's equal to 1,000 times the Laplace transform of the input. This is now a frequency domain relationship between the input and the output, and it has all these multiplications by s's and some constants. But remember what happens in the time domain when we have in the frequency domain a multiplication by s. Multiplication by s in the frequency domain corresponds to differentiation in the time domain. If we now multiply by s cubed, that now says, oh, that's the same in the time domain as differentiating y 3 times. Then we have 20 times y differentiated twice, plus 200 times y differentiated once, plus 1,000 times y of t, and all of that's equal to the right-hand side, which is 1,000 times x of t. That now produces this differential equation relationship between the input and the output for a third order low pass filter that has a bandwidth of 10 radians per second. We'll pick up at that point next time.